Good afternoon, my name is Zaid and these are my colleagues ID and Roman, and we are going to do sustainable development for the SEQ building. So the Seneca Committee initiated a sustainable development project across all their campuses, and in our case we're going to talk about the SEQ building, which is the main building of the Seneca York campus, and it was constructed in 1999. Our project objective is to analyze, design, as well as critique new proposed design for the SEQ building, as well as apply a life cycle analysis for the prior design as well as the new design. So approximately 29% of domestic water uses comes from the toilet flushes, as well as 5% from toilet leaks. And in the case of the SEQ building, it uses standard toilets which consume about 3 to 5 gallons of water per flush. So as urban development increases, the loss of green space also increases, and this can be very detrimental as the increase of managing stormwater will also increase. And the SEQ building does a very good job by retaining green space around the building as well as in the courtyard. Similarly, urban development also increases localized weather, and this is referred to as the urban heat island effect. And as mentioned earlier, SEQ building is designed to maintain as much natural green space as possible. So for different building materials can alter the way the energy is either consumed or conserved, and through the choices of material regarding energy, it can either prevent thermal energy from escaping or entering the building. And based on the selection of the material, we can either help reduce or increase the energy efficiency. And SEQ building is designed to be a very high energy efficient system. This is due to the low wall to window ratio, enhanced interior and exterior building, as well as the material used to save thermal energy. For passive energy systems, it requires the use of environmental energy sources to power the building. This is featured on the high to window to wall ratio, which allows for exterior insulation that reduces thermal energy loss, as well as ambient exterior lighting. And on the other hand, active energy systems is purchased energy sources to power the building, and this is seen through the HVAC systems of the building, which recover heat and moisture that can be used to change the temperature of the building, as well as use fresh air from outside to reduce cooling costs and increase air quality.
Thank you, Zaid. Now, although the building was designed properly, it's still not deemed sustainable. So in order to help us design a sustainable, proper building, we turn to the LEED body, which stands for the Leadership in Energy and Environmental Design. It's one of the most famous green building rating system in the world. They have different score badges that goes from the certified badge, the platinum badge, silver and gold as well. So you just amass different points on your recommendations and implement them, and you can score a good badge on anyone. So for our department, we're basically proposing a major renovation. So we turned to LEED website and we got these credit points, which are classified into various classification segments. That included location and transportation, the sustainable sites, water efficiency, energy efficiency, material and resources, amongst other things. Now we turned that into an Excel file and we're able to amass different points that we're able to recommend. And in total, we're able to recommend about 51 points, which puts us in the silver category. Now Roman's going to talk about the life cycle assessment and how we could implement these recommendations into the real life.
So first we conducted a life cycle assessment on the current building as it stands right now. Obviously with any construction process, it involves a complicated procedure of acquisition of materials and assembly. So in order to analyze these kind of materials, we searched through Seneca College for floor plans, as well as on-site investigation to see the type of columns, beams, type of reinforcement that was being used. And obviously we had to account for the current energy use as it stands today. So first we were able to conduct the bill of materials report, which I said previously, which includes the type of reinforcement, concrete, all the type of beams, current installations being used, and so on. That was inputted into Athena. And now moving on to the current energy use, as you can see in the second figure right there. All of that is in kilowatt hours per year. We also inputted that into Athena, and we also gathered the square footage of the building. Now what Athena does, it takes all the inputs, as I said before, it analyzes it through a bunch of construction algorithms incorporated into the system, which outlines the type of construction mainly used in North America, namely Toronto, and it outputs the fossil fuel use for both embodied and operational, as well as global warming potential and things of that nature. The first major result is the global warming potential, which is basically the quantified measure of the amount of heat that is trapped in the atmosphere by any given gas as it relates to CO2. Now, for the Seneca building, currently it stands at 152 million kilograms of CO2 equivalent per year, and which, according to EPA, if a car takes about 4.6 metric tons of CO2 per year, it is the equivalent of operating 34,000 cars every year. Now, for the fossil fuel consumption, we have almost 2 billion megajoules per year, in addition to non-renewable energy of almost 4 billion megajoules per year, and finally the total primary energy consumption of 4.2 billion megajoules per year. Now, from those results, we can see that the vast majority of environmental impact stems from operational use of current heating, ventilation, and electricity within the building. So this is the sort of area that we have to tackle with our sustainable measures.
Now, taking in all this information and going back to our LED renovation checklist, we were able to deduce a couple of LED recommendations that could be done to the building. One of them included insulated walls. Poor insulated rooftops are detrimental to the building lifespan, and Seneca has one of those. It forms ice dams and the snow melts, which damages the exterior of the building. If you're going around there, you could actually see that already affecting the building. And this would also increase energy efficiency in the environment, as it will amount for about 80% of heat loss recovery and make it more energy efficient. Another one we recommended was indoor motion sensor lighting. Not only does this save energy by only activating when there's someone in the building, but it also observes the external ray of light coming into the building, and that way it could it could reduce its energy consumption and dim the lights a little bit if it's a sunny day, for example. Another one was the LED recommendations, which also score points in the LED checklist, and one of them was permeable pavement. Personally, I remember going across SEQ building last summer, and they were implementing just asphalt pavements that were totally non-permeable. This interlocking pavements would help with infiltration and would also prevent things of like flooding and erosion and things of that nature. Another LED recommendation was the implementation of a vegetated roof. At the moment, SEQ building only has a concrete roof, which doesn't help with flooding and all those things that the vegetated roof would help with. And for us, we're proposing the implementation of a green roof that would also store the water, and that way we could use that for high water efficiency system in our toilet system, which would store the water at the roof, and then we'd use that in the toilet, as you can see over there in the image over there. This would help reduce 73% of the water currently being used by the building.
Okay, so the measures that we could assess using Athena, we incorporated the insulation into the additional materials, as well as the adjusted energy consumption provided by the occupancy sensors, and we're able to get a 20% reduction in the embodied global warming potential, as well as a 21% reduction in fossil fuel consumption, in addition to 18% reduction in non-renewable energy use, and finally the 12% reduction in the primary energy consumption. So to put that into perspective, these are all the results that are outlined here. And finally, to summarize, ceiling insulation was used as well as indoor motion sensors, various LED systems that were outlined by my colleagues, a vegetated roof, and a total score of 51 points, which gave us a silver certification. Thank you very much.
Thank you.